So there are these divergent integrals that we evaluate by analytically continuing to lower dimension to 4 minus epsilon dimension. And the simplest of these integrals that one comes across has this form. As Wonjun pointed out, if you redefine, in the denominator, if you complete the square, so this is what happens to your denominator. Then if you define a new variable p prime, right, which is p plus q, then this integral becomes independent of the angles. And you can then go and do the integral, and that involves gamma functions. And the final result is of this form. So there are several other integrals that we'll need. Okay, before I do that, let's just review how this leads to the regularization. So alpha is a positive integer. So for small enough alpha, say alpha equals to 2 or less, if d is 4, we see that the argument of the gamma function is a negative integer. And that's basically the divergence. So one way of getting rid of the divergence is to say that, how about we take our space-time dimension to be 4 minus epsilon, and then the gamma function in the numerator has the form of some negative integer n, which will depend on alpha, plus epsilon, and then we can then do an expansion of gamma function, which you can find in special functions books. Which will involve some constant psi1. And this part is the divergent piece. And so which is basically a pole in the gamma function, right? So this is how we isolate the divergent integrals, the divergences in our loop Feynman diagrams. So that's not the only form of the integral that we get. We often get some other forms of integrals, and I'll just write down the integrals that we'll be using today. There's a complete list of the integrals that you will need for 4-dimensional calculation is given in the appendix of Peskin and Schroeder. So we also need, use integrals like these. Sorry. So there's a p squared minus delta n, some positive integer, and this gives me n minus 1 4 pi d by 2 I d by 2 n minus d by 2 minus 1. And then we'll also need a tensor integral of a tensor quantity, which is simply p mu p nu divided by p squared minus the n, and n minus 1 4 pi d by 2 I g mu nu, the flat metric, Minkowski metric, and I forgot a factor of 1 over delta here with the power of n minus d by 2 minus 1. Similarly here. Right. Ow. So, anticipating the fact that we'll be regularizing our theory in a dimension which is other than 4, let us now rewrite the QED action in some arbitrary dimension d. And then we'll take d to be 4 minus epsilon. So our QED Lagrangian in some d dimension it's the same Lagrangian with one important difference, is that the dimension of these quantities will now be different. And we'll do the calculation in what is known as the Feynman gauge, which is one of the special gauges which are Lorentz invariant. So this is the gauge fixing term. So apart from this term, the whole Lagrangian is gauge invariant. Now, as usual, we play the game where we say that our Lagrangian in d dimension has dimension of d, and therefore, our field, the fermion field in d dimension, has dimension of d minus 1 by 2. Our electromagnetic field has dimension d by 2 minus 1. Now, we're going to organize perturbation theory in powers of e squared. And because we want to do that, we define our E to remain dimensionless, right? So for this term, now to have dimension D, we have to introduce a new dimensionful parameter, mu. We don't have any choice in this if we want to keep E dimensionless, because the dimension of A, psi, and psi bar are fixed by the kinetic term, this one and this one, right? So mu is some dimensionful parameter. It's a mass dimension, has dimension of mass 1. Now this has a name. One name is, it's the subtraction point. Subtraction point. Or the energy scale. However, one has to realize that this mu is an artificial parameter we're introducing, and the physics at the end of the day should not depend on mu. And requiring that the physics does not depend on mu at the end of the day, we'll see that it leads to all our physical quantities depending on the energy scale at which we are doing the experiments. So, things that we classically thought of as constants, such as mass, electric charge, those things will now have a dimensional dependence. Sorry, a dependence on the energy scale. Sorry?
With the coupling in front of the f squared, wouldn't that be like in François' lecture we had 1/4 e squared in there?
Right. So you can rescale the a to to bring it over here or absorb it here. So yeah, that's you can always redefine your f in that way. And that's especially useful because in Yang-Mills, that's useful because in Yang-Mills, the gluons will interact with each other. So you want some G in the in the definition of, well, F, I guess, because then you can keep track of perturbation theory for gluons as well. Okay, so we'll come back to this. Now, because we will analytically continue the momentum integral to some d minus epsilon, 4 minus epsilon dimension, but some of our amplitudes will have traces, and whenever you take traces of gamma matrices, you know that the dimensions sort of crop up because they're 4x4 matrices. So we actually have to generalize some of those identities for the gamma matrices. So we start with gamma, the Dirac algebra. And then, for arbitrary dimensions, you can derive that the Dirac algebra should give this. So this guy will come from some tracing of eta. Sorry, I'm interchanging eta and g. I'm using eta and g interchangeably. So in 4 dimension, the identity matrix acting on spinors in 4 dimension will give you 4. But in arbitrary dimension, what we require it is that we require it to be some smooth function of d, such that when d is 4, this guy is 4. So this is the trace. So then, using the Dirac algebra and the trace, we find I should really use just this guy, and then there is also the trace of the 4 gamma matrices. It's kind of, the generalization is obvious, but let's just write it down anyway. So previously there was a 4 here, but now there's an f of d times the usual stuff. Okay, so today's lecture will be a little technical, but that's the nature of the game. Yeah?
Is there any reason why we do not naively say f of d is d? Like, it's very tempting to write down f of d is
No, because in a higher dimension, you know that so in say 6th dimension, your gamma matrices are they're 2 to the power 3, 8-dimensional, right? So there it would be. So I mean, maybe you can do something like, yeah, there it would be 6, right? Sorry, it wouldn't be. It would be 8, right? So yeah, because it's only it's a coincidence that's in 4 dimension. The Dirac matrices are 4-dimensional, essentially. All right. So gamma 5 does not generalize to arbitrary dimensions. And that's because in the definition of gamma 5, there was and this guy is intrinsically, the epsilon tensor is intrinsically 4-dimensional. And the fact that this doesn't generalize to arbitrary dimensions, I'll just point out in the relevant at the relevant point in the lecture, is related to the fact that there is this thing called chiral anomaly in theories where you have left-handed or right-handed fermions. Okay? Essentially, it'll boil down to the fact that you cannot write a counter term which cancels a certain divergence. Okay, so let us look at the divergent diagrams now. So first, the electron self-energy diagram. So this is something like this. So you have some momentum P coming in, some momentum P going out. It's charged, so the momentum in the loop carried by the propagator is P minus K, and the momentum carried by the photon is K. So remember that we derived this superficial degree of divergence, which for QED was in 4 dimension was 4 minus 3, the number of external electron divided by 2 minus the number of external photon. So if I use this formula on this guy, it tells me that this should be a linearly divergent diagram, right? But we'll see after careful analysis that this is actually logarithmically divergent. And that's why it's a superficial degree of divergence, not a deep degree of divergence, right? So what is the amplitude associated with this diagram? The self-energy is minus IE squared. It's the same thing as you would write down, but now because you have this extra factor of mu here, your Feynman rules must include that. So there'll be 2 factors of mu to the power 2 minus d by 2. That'll give you mu to the power 4 minus d. And then you have an integral over the undetermined momenta. And there's that vertex gives you a gamma mu, and then the fermion propagator and the other vertex. And because we are in the Feynman gauge, this is our photon propagator. Okay. Now, what we want to do is that we want to combine these 2 denominators into one expression. And so there is a trick originated by Schwinger, but known as the Feynman trick. And according to some physicists, the reason for that is that nobody could understand Schwinger's papers anyway. They were so technical. So I want, I call it the Schwinger-Feynman trick, or so of combining different, denominators. So for two denominators, the formula is, so we have A and B. A is this guy, and B is this guy. We can combine them into, by introducing this new, the Z parameter is called the Feynman parameter. So this is very easy to verify that this holds true. And again, there are generalization of this thing for combining more than two denominators. And again, you can find that in the appendix of Peskin and Schroeder. For today's lecture, we won't need to combine more than two denominator. I think for Dan, you will need, so Dan will introduce the generalization of this formula. So, right. So we use this now. And so our self-energy of the electron now becomes P slash minus K slash plus M gamma mu divided by P minus K squared Z minus M squared of Z plus K squared 1 minus Z. Right. Now, if we expand this, then the K squared Z terms cancel, and then what we have left in the denominator will involve some K squared and, some terms involving K, but then we can actually introduce a new variable, which we call K prime, which will allow us to, complete some squares and rewrite this integral in a way such that the denominator only now depends on K prime squared. So if we introduce this variable, then this thing becomes d to the power d of K prime 2 pi over d gamma mu P slash minus P slash of Z minus K prime slash plus M gamma mu divided by K prime squared minus M squared of Z. So my squares look like V's, plus P squares Z 1 minus Z, this. So now there are 4 terms, but this term, because now the denominator, the K dependence, is this simple K prime squared, the term which is linear in K prime in the numerator will drop out because it's an odd integral. And so, I'm going to be pretty horrible and erase this term, okay? But this term is there, but then it goes away because it's an odd integrand, right? Now, if you now stare at this expression, you see that your denominator for large values of k is just k prime to the power 4, and in 4 dimension this will be d4 of k. So this is a logarithmically divergent integral, right? Not the linearly divergent integral that the superficial degree of divergence told us about. So, so now you basically, we use our identity involving the gamma function, and then we can we can express this integral there's a gamma of epsilon by 2, and then there's an integral over d of z, which is very easy to do, but I won't do it. So this is a bit messy looking expression, but we won't have to deal with the whole mess.
Sorry, one question.
Yeah?
From the volume element, if we do this integration, don't we get a k prime to the d minus 1? So that's not necessarily odd or even, it depends on which d we're living in, right?
Yeah, no. Each element, just think of it in Cartesian coordinates. Then each component of the integral, gives you.
Yeah, because I was talking about radial ones, but they were always quite.
Right, yeah. And so, okay, so we have m squared. I'm going to raise the board so you can see this part. Right. So now, what we're interested in this integral is the divergent piece. And to get the divergent piece, we now use the fact that our gamma function has this expansion where the pole is 1 over epsilon minus the Euler-Mascheroni, sorry? Mascheroni coefficient, constant. Okay. Right. So if you now plug this into, into the expression, and then, just do the z integral, because the z integral is very easy to do, you basically get the divergent piece, which we will be interested in right now. I see that I have made a mistake in my notes, that I have written 8 pi epsilon squared. It should actually be 8 pi squared of epsilon. Let me just make sure. Yeah, right. All right. So yeah, so this is minus p slash plus 4m, and there's a part which is finite, as epsilon goes to 0. So we have succeeded in isolating the divergent part of the photon, of the electron self-energy diagram.
But how can our self-energy
No, the electron propagator is a matrix.
Yeah, but I mean, the self-energy, isn't it just some addition?
Well, this is self-energy. We call it self-energy because it's a correction to the bare propagator of the, and that's why we call it the self-energy. Yeah. I mean, classically, of course, self-energy is not a matrix. The name comes from the classical self-energy of the electron, right? So next we look at the photon self-energy diagram, also related to vacuum polarization, sometimes called the vacuum polarization diagram. And so some photon is happily going along, and at some point it emits a positron and an electron. So this is the so there are some indices. And there's a momentum flowing like P minus K. So this contributes a correction to the bare propagator, and this is something I did yesterday. Is the exact Feynman propagator would be a perturbation series. So this is the tree-level propagator in the Feynman gauge. And there would be some correction, which would be the leading order correction to the 1 pi for the 2-point function, and higher loop corrections. So this is basically will be given by that diagram. So what is it? So during QFT1, in one of the tutorials, there was an optional question about, how what the Feynman rules are for fermion loops, and essentially it involves introducing a minus sign and taking a trace. So this guy, which is a function of the external momentum k, has a minus sign coming from the loop, and 2 powers of these guys coming from the 2 vertices, the momentum integral over the undetermined momentum p, trace over the spinor indices because the external state doesn't have any spinor label, the 2 propagators for the spinors, gamma matrices for the vertices, so pretty simple. Now we now introduce the Schwinger-Feynman parameterization, and then I defined something called P prime, which is P plus kz minus of k. So if you do this, then pi mu nu of k becomes, and I think I've been very careful about the factors of i's and minus 1. So I think there are 4 i's on the right-hand side. They all cancel out. and then there's a minus sign, and there's an I here. So when you bring that I over here, it becomes plus I. Okay, yeah. So I E squared. There's going to be an f of d from the trace, and then mu of 4 minus of d d to the power. So I'm just not going to write p prime, but this is p prime, but I'm going to switch to p, the notation. And then we get 3 terms. This is going to be the important term. And then we have another term which is just g mu nu in the numerator. And in the denominator, we have this guy. But now what is important is that this guy has, it's not square here, it's just 1. Okay? So now at the beginning of this class, and close brackets, at the beginning of this class, I gave you the integrals involving Gauss function, and if you use those integrals, you can show that this guy will cancel this guy. Okay? So what's left is this thing. And then again, we can say, okay, what kind of divergence, what kind of divergence is it? Then again, in the denominator, we have p to the power 4. And in 4 dimensions, this would be d4 of p. So we see that this is, again, a logarithmic divergence. But if you had gone to your formula, which was 4 minus 3 electron minus, was it 2 or, yeah, 1, p photon. So this was 0 in this case. There's no external electron. So there are 2 external photons, so this would be 2. So naively, you'd think that it's quadratically divergent, but in reality, it's actually logarithmically divergent. All right, so what's the final result if you do the p integral? So if you do the p integral, we have k mu minus g nu k squared. The fact that we have this factor multiplying everything tells us that gauge invariance is preserved, because this is basically the momentum space representation of the differential operator which appears in the kinetic term of the gauge invariant part of your Lagrangian. Right? So essentially, the F mu nu, this thing, you wrote this as some operator like this, and the propagator is just the inverse of this operator, right? And this is the momentum space representation of that operator. Okay, so let us finish with, so the divergent part is this guy, and there's this other stuff which I will write down for completeness. Or in other words, we have E squared by 6 pi squared epsilon. So this 3 multiplies this 2. And then K mu, K nu, minus G mu nu, K squared, plus a finite piece. Yeah, you're right, sorry, yeah, so, yeah. According to my notes, yes. Okay, so gauge invariance, means that the divergent part is 0, and this is related to this is essentially the fact that your momentum this differential operator has a zero eigenvector, right, which is K mu.
Is there the reason why we only pick the divergent part? Like there's one identity, right? So
So the renormalization prescription that we'll use only cancels the divergent part. There is no reason why that should be the case. There are other renormalization prescription which will say, you cancel the divergent part and the finite part as well. You can always do that. And the physical result should be independent of your prescription. But yeah, I mean, this is, the fact that the divergent part has this form means that when you are actually adding a counter term to absorb this divergence, that counter term will also have the same form, will be gauge invariant. So that renormalization does not spoil gauge invariance. And because, you can think, say, for example, if you look at the electron self-energy diagram, right, it tells us that, you will see that it tells us that we have to introduce a mass type of counter term in our Lagrangian. So even if you started with a massless theory, you would generate mass by that diagram. Whereas what this is telling us is that the divergence is of such a form that even quantum corrections will not, generate a mass for the photon. Okay, there's a few other diagrams that I will mention which will look divergent, but they are not. And I'm not going to prove these statements. Some of these statements are pretty non-trivial to prove. So before I move on to the diagrams which are not divergent, let me just flash the third diagram, which is divergent. And this diagram, although its finite part is very important in some calculation, and especially in a computing G-2 and some infrared effects. So Dan will treat this diagram very carefully. So the third is the vertex correction. So the vertex correction. So some P coming in, and then some Q going in like that, and a P plus Q is P prime going out. So Dan will actually, I will give you the divergent part of it in a moment, but Dan will treat this more carefully. But there's also the tadpole diagram. And some of you in the QFT1 interview were asked to compute this diagram. And I can see Pratik smiling. And this is actually 0. It's pretty easy to show that this is actually 0. And then some of you in QFT1 interview were asked to write down the expression for photon scattering. Two photons come in, they exchange some fermion, and it's pretty involved, but you can show that this is actually not divergent. There are also triangle diagrams. And in QED, they always come in pairs. You can show that these two things are not equivalent, and they cancel each other out. However, in theories where you have left-handed Weyl fermions or right-handed Weyl fermions, they don't come in pairs and they don't cancel each other out. In those theories, you have to renormalize these diagrams, and and you'll see, and if you do that, you'll see that they involve, because those theories have a chiral current, right? A current which is of this form. And so basically, gamma 5 enters this computation, and one of these diagrams lead to the chiral anomaly in that case. Okay. The fact that in QED this thing vanishes is related to the fact that QED is invariant under charge conjugation. So this is analogous to the phi cubed theory. The phi 4 theory being invariant under phi going to minus of phi. And the vanishing of this diagram is known as Furry's theorem. It's not a Furry theorem, it's Furry's theorem. Okay. So what's the joke? Oh, I see, okay. I think many people have pets called furry, right? So if I could prove the theorem, I would name it after one of my cats. Gordon's theorem.
Sorry, Tibor, what's the statement? You said that if there is no chiral current present, then they cancel each other, or what did you say?
Right. So the statement is that suppose you have a theory which has only, say, which is chiral, right? Then suppose you have only left-handed valve spinners, right? Then in such a theory, this, this diagram will actually lead to an anomaly. So if you have just say valve spinners, say left-hand valve spinners, you will have a you'll have a conserved chiral current, and this diagram in that case will potentially lead to an anomaly in that current. It may be the case that when you take into account all the matter content in your theory, that these anomalies all will cancel out, right? And I think that's what happens in the standard model, right? In the weak sector, I think, yeah. That there is a potential anomaly, and that actually is canceled out by when you. But I don't remember the exact detail of that. But Fari's theorem is just like about QEDs, and in QED these two things cancel each other out. Okay, so now that we have we have identified the divergences, we are going to do renormalization of QED using counter terms. So our next topic is renormalization. Using counter terms. I think you saw some of this in Dan's tutorial and also in Francois' lectures. You also saw a renormalization using hard cutoff. The hard cutoff doesn't respect gauge invariance, so it's not the preferred method for using in QED. There is another method called the Pauli-Villars, which does respect gauge invariance, but that doesn't generalize to non-abelian gauge theories.
When does why hard cutoff does not respect the gauge invariance?
Well, it's because essentially because hard cutoff is kind of you're saying that I'm throwing away all the fluctuations which are smaller than a certain length scale. And gauge invariance is related to space-time transformations. So those two things turn out not to be, consistent with each other. So,
when I write down the action,
right?
What we only do is we only restrict the range of interval, isn't it? Use the hard cutoff. What we only do is we never touch the action, but we only change the range of interval. So isn't that gauge invariance intact?
No, I mean, I think a lot of times when you do these, when you're writing or rewriting this formula, you actually throw away some boundary terms. And I think it's really, so I mean, I have to check, I may be wrong, but I think when you're throwing away those boundary terms, what limits you put in the integral is actually matters, right? And I think that's when it comes in that you actually cannot do that. All right, so these are our divergences at one loop. The self-energy of the electron, plus finite, this is reminiscent of the OPEs in CFT, right? Have you guys seen the OPEs in CFT yet? Okay, where you're basically looking at the and then Dan will show that the divergent part of the vertex correction, which is sometimes denoted by lambda mu 1, there is a finite part which is denoted as lambda mu 2, is okay. So the philosophy is that we saw that our original Lagrangian, which I seem to have erased, led to divergent contribution at one loop. So the idea now is to add to this original Lagrangian a new Lagrangian, which is formally infinite, which means that when you take the epsilon go to 0, that Lagrangian is going to be divergent. But that Lagrangian, the contribution of this extra Lagrangian, are going to cancel the infinite contribution at one loop from our original Lagrangian. So basically, we are going to have some total Lagrangian, which we will call, say, bare. This will be the original Lagrangian plus a Lagrangian which of counter terms. So let's consider that there are three sectors in our Lagrangian. One is the free part of the fermion fields. There is also the free part of the photon and the gauge fixing term, and there's also the interaction term. So let us write down those Lagrangians and the counter terms for those Lagrangians one by one. Okay. So let's call L1 our original Lagrangian, which just involves the free part of the spinors of the fermions, and the tree-level Feynman propagator came from this part of the Lagrangian, right? And the divergence number 1, that was a contribution, that was a correction to just the free Feynman propagator. And if you look at the divergent part of number 1, you see that the coefficient of P slash and M are different. So that means that whatever we have to add to this Lagrangian to cancel that divergence, the coefficient of the kinetic part and the mass term has to be different, right? So the counter term that corresponds to this Lagrangian is right? And so the total Lagrangian, which we will call L1b, B for bear, not the animal, will have this form. What are the z's? So by the way, this is the whole thing is the counter term, not the z's, right? So this is also the sorry. What I mean is this whole thing is the counter term. Right? So the z of psi is just 1 minus e squared 8 pi squared of epsilon, because that's what you need to cancel the first divergence in number 1, and then z of m will be 1 minus e squared by 2 pi squared of epsilon. Now we can re-express this Lagrangian in terms of objects which are divergent formally. So we can say L1 of bear is is psi bar of bear times del slash psi of bear minus m of bear psi bar b of psi of b, where psi of b is square root of z psi of psi, and similarly psi bar of b. And the mass, the bare mass, is now given by, Zm by z of psi times m. And this is sometimes written as m plus delta m, where this m is the original, finite mass, and delta m is the infinite correction, the divergent correction. Now, since we are only interested in, at this level, like this Lagrangian is, this Lagrangian is of the order of e squared. If you look at the expression for z's, these have e squared, and the ones are canceled out by these ones, right? So, since we're only interested in quantities up to order of epsilon squared, we can now expand these guys out. Then the bare mass turns out to be 1 minus 3 e squared by e pi squared epsilon of m. And they're higher order terms. So now that we have added new terms to our Lagrangian, we have to add a new Feynman rule for them, right? So you can actually think of these guys as kind of an interaction term. And the Feynman rule for them is so the Feynman rule, and this is, this is a rule that comes in at one loop level. Well, of the order of epsilon squared in the perturbation theory, that if your incoming momenta is p and outgoing is p, then you write for this guy I of z psi minus 1 of p slash minus I zm minus 1 of m. So when you're doing calculation, so you're so for example the total Feynman propagator now, at the tree level you have the tree level propagator. So this is of order e to the power 0 that we all know and love. And then there's the diagram that that we calculated, which comes in at one loop, which is of order e squared. And this was this is the integral that we evaluated. But because now we have a new terminal Lagrangian at e squared, at the order e squared, we have to now add that diagram as well. And for this diagram, for this term, you have to write down this, you have to put in this expression in your amplitude. And what this amplitude does is that the divergent piece of this thing is now canceled by the divergent piece of this. Okay? So the counter terms that we have chosen have this form. In general, order by order in perturbation theory, there will be higher, the counter terms will have this form. There will be some coefficient, and e squared to the power n, and there will be epsilon to the power n. And what we have done is that we have only calculated n equals to 1. So so this choice of counter term, which cancels out just the divergent piece in our, in our 1 loop and 2 loop or 3 loop calculation, this prescription is known as the minimal subtraction. And for conceptual purposes, this is the simplest to introduce in this class. But if you look at a lot of the renormalization literature, you will see that the z there defined has a finite part. And if you go back to this integral that I showed you, that integral had a divergent part plus some messy part which was finite. And what it does is that there are subtraction schemes where the z actually cancels this other kind of, this finite part too. And one very popular scheme is called MS bar scheme. And also another thing is that, as you go to higher and higher loops, you will have more factors of 1 over epsilon, right? So the power in the epsilon is related to what loop, it's the divergence is related to what loop you're working at. So, the physical mass is given by the pole of the propagator, right? So, the inverse propagator, our 2.1 pi, which was IS prime, the exact Feynman propagator inverse. This has now the free part minus m, and then there was the divergent part, but that's now canceled by the counter term contribution. So there will be some finite terms left over. So m now is basically, we call this the renormalized mass, and this is shifted by a finite amount from the physical mass, which is the pole of, which is the 0 of gamma 2. There are subtraction schemes in which the renormalized mass is equal to the physical mass you observe. But we are not going to be talking about that. But I just wanted to point that out. That the fine part, yeah. All right, so next we where should I go? Let's go here. So next we discuss the photon self-energy diagram. So this had the form of e squared minus 6 pi squared epsilon, and this depends on k mu, k nu minus g mu nu, k squared plus some finite piece. And this corrects the the tree level propagator, the Feynman propagator at the tree level. In this way. So now if you actually write down the correction, this guy, including the finite piece, and do this algebra in the Feynman gauge, you get the result that the Feynman gauge, the tree level Feynman gauge contribution, corrected by a divergent part and a finite part, which nonetheless goes to 0 in the limit k going to 0. And then another divergent part, which takes you out of the Feynman gauge. So the form so what this means, this extra term, is that when you're adding counter terms, the coefficient for the gauge invariant part and the part which fixes the gauge will be different. It's similar to the it's similar to the photon the electron self-energy. And so what are Lagrangians for the? So L2 is minus 1/4 of f mu nu minus, in the Feynman gauge we added this guy. And the counter term is going to be, I call this ZA minus 1 by 4 f mu nu. And there is some constant, some other counter term here, which is related to the fact that we are in the Feynman gauge. Because this is a gauge-dependent counter term that I'm not going to write down explicitly what it is. It's easy to work out. the gauge independent part is this. So now if you define a bare field, then your total Lagrangian, which is L true bare, will have this form. And your Feynman rule so for the gauge invariant part, your Feynman rule will be given by just this, your new Feynman rule. In the Feynman gauge, I haven't really worked this out, but you would, this would give you some other, the counter term delta 3. Your Feynman rule will be something like this, where delta 3 you can easily work out. But the point is that the gauge invariant part has this k squared g mu nu k mu k nu term, which comes from the fact that this thing it satisfies this, right?
Are we having two different kinds of counterterms?
Yeah, if you have there would be a gauge independent counter term, which is like the first guy over here, ZA minus 1, and there's the one which will be the gauge dependent counter term.
Then when we draw the diagram, like we have to
distinguish.
Yeah, distinguish the.
Right. No. So I gave this in case you want to use a different gauge. Whatever gauge you choose, you will have to work out what the gauge dependent counter term is, right? And then you have to work out what the Feynman rule is for that guy. For the Feynman gauge, you don't have to use this, you just have to use this for a delta 3, which I didn't bother to work out. Okay? Yeah?
Where did the E go?
Where did the E go?
Yeah, where did you fix the in the bare Lagrangian L2? Why don't we have a gauge fixing term?
Well, right, E, the big E.
Yeah.
The big E is determined by well, that is the gauge fixing term.
Where did it go?
So where did it go?
And like in the bare Lagrangian.
Oh, I see. Oh, so yeah. Sorry, yeah. No, there should be. Yeah, I'm sorry. Very, very good. Thanks. Yeah. So plus a gauge, gauge term. Yes. Yes, there should be. Yes, I forgot that. Yeah. So the last piece for our counter term is the Lagrangian that we are starting with is the interaction Lagrangian. And this has this form. And the counter term that we add is some ZA minus 1 E of mu 2 minus D by 2 psi bar A slash of psi. Right, where ZE is 1 minus E squared by 8 pi squared of epsilon. And then we also have a the Feynman rule that for this we have to add 1 minus E Z of E minus 1. So putting all of this together, the bare QED Lagrangian is going to be this. It's just the QED Lagrangian but with B on everything. And everything is infinite, so that at one loop things are finite. Plus gauge fixing. Here, the EB is a new quantity that is defined as E mu epsilon 2 ZE by Z psi square root of ZA. And because we're only interested up to order epsilon E squared, this turns out to be that this thing. I think that's correct. All right, so let's recap. Which board am I going to use? That one. So these were the divergences that we needed to cancel out. And for those, we had to introduce 1, 2, 3, 4 counter terms, plus 1, which was gauge dependent. And these 4 counter terms that we had to introduce to cancel the divergences were this guy's for the mass term, we had to introduce this thing. And for the interaction term, and this thing is actually at this order equal to z psi. And this is actually true to all orders. And I think you have to use Ward-Takahashi identity to prove that. Schwartz gives a proof. Now the final part of today's lecture, I'm just going to talk about, how the dependence on energy scale enters. So the procedure of renormalization involves introducing an arbitrary mass scale or a momentum scale mu. I'm going to keep using that side because, sorry. Because I just wrote this. So, this thing mu that we introduced, although it's arbitrary, in general, we want to choose a value for mu which is at the same energy scale as the processes that we are interested in. And you might say, why is that? Well, the reason is that if you look at the finite corrections, the finite corrections will have some form like something like this to our amplitude, and to small, for small epsilon, this is what is this? This is e to the power log of mu epsilon. So 1 plus epsilon log of mu. And this will be multiplied by some divergent quantity at one loop, which is 1 over epsilon. So that will cancel this 1 over this epsilon. And so the finite part will have a log of mu dependence.
Is it the same mu that we had all this time? Because
Yeah.
that was just the one that we used to make e-dimensions.
Right.
How is that related to some intrinsic energy scale? I don't see this.
Well, yeah, we'll come to that.
Oh, okay.
We are trying to, it's but okay, so at the end of the day, we'll be computing some cross sections. In principle, you would be computing that to all orders in perturbation theory. But of course, we cannot do that. And this should be independent of any mu. But since we are mortals, we can only calculate term by term in perturbation theory. Things on the right-hand side, individual factors will depend on mu. So there is some, and in general, the structure of our cross sections will, in perturbation theory, will have some form like this. There is some coefficient, a numerical coefficient. There's a typo in my notes. There should be an n. I wrote 2 here. And then there would be logarithmic corrections which are mu dependent, which also involve the energy scale, and then some subleading term at that order. So we'll see in a moment that, so the E squared is the renormalized coupling. We'll see in a moment that it's actually also depends on mu. So, but what is interesting here is that for this sort of perturbation series to converge uniform, in some in a way that will make your calculations easy, you want this mu to be of the same order as S. So this is just to motivate why, even though you can take mu to be anything, it's like the mass of an elephant, you want to choose mu which is of the same in the same energy scale as your typical processes. So if you're doing QED, for example, you can choose mu to be some near the mass of the electron. And for, say, standard model calculation, it could be the mass of the Z boson. And that'll just make your the convergence properties of your formulae more pleasant. But see, our bare Lagrangian, which, although is formally infinite, is the boss Lagrangian. This is the one which will give us all the physical quantities which are finite. And therefore, a bare Lagrangian, all the quantities there should be independent, be required to be independent of mu. Okay. And this is where the sleight of hand comes in. And that means that if I take the derivative of the bare coupling with respect to mu, it should be 0.
Dimensionful constant for the regularization.
Right.
But is that also related to the renormalization scale you're fixing?
Yes, that is the renormalization scale.
Is that mu is the renormalization scale?
Right. But then there's going to be something, the energy dependence will come because, as a result of that as well. Okay, so I mean, okay. So, I'm not going to spend a lot of time on this, although this is conceptually very, very subtle. And I would just go back and think about the renormalization of the coupling constant in the phi to the power 4 theory that Francois did. And there you also saw that there you had a cutoff, and the cutoff there is the, it's the analog of mu, that when you introduce the cutoff, your amplitude became dependent, on a momentum scale, because you defined some physically measured coupling constant at some given value of external momentum, right? And then you required that that your physical quantities do not depend on the exact value of the cutoff, and that implied that the coupling of phi to the power 4 theory became a function of the momentum scale, and that it actually changed with the momentum. And although you measure it at some particular momentum, you can find out the value of the coupling at any other momentum by solving the differential equation that is satisfied by that coupling, right? So here, so the the mass scale mu, the momentum, the renormalization scale mu, allows us to derive that momentum dependence, that energy dependence of our coupling, even though the physics is actually independent of the particular parameter we choose. So how do we do this? The bare, the bare coupling constant is given by E, which is the renormalized coupling constant, times mu by 2, 1 plus epsilon squared, 12 pi squared of epsilon. So this is our formula. Now, we take the logarithmic derivative of this. And in the limit where epsilon goes to 0, this should be 0, right? So if you apply this to this formula and keep terms up to to order E squared, then you find that mu, that the logarithmic derivative of E is given by this thing, where we have taken the limit of epsilon going to 0. But the left-hand side is what we call a beta function. And this is the beta function for QED. So one can now, this is the one-loop beta function for QED. Because E physical is related to the renormalized E by a finite shift, because E now depends on the energy scale mu, the E physical will also depend on the energy scale. Right? Now you can solve this differential equation, and you find that the E at some energy scale, mu, is given in relationship to E at a different energy scale through this formula. So now we are now considering this. We are now treating the mu dependence as the dependence on some physical energy scale. So now suppose you do some experiment, say at some energy scale mu naught, and you find that your coupling at that mu naught has some value, say 1/137 or something. Then your theory will tell you what the value of that coupling is at some other energy scale through this formula. Okay. So although the renormalization scale is an artificial scale, it allows us to derive the energy dependence of our physical quantities. One interesting aspect of this formula is that this has a pole. And if you plug in, when this thing goes to 0, if you plug in the observed values of mu naught and E, say you measure some mu naught, it turns out that the pole is at some energy of 10 to the power 286 electron volt. This is known as the Landau pole. So it's like much higher than even the scale of quantum gravity. So there is no reason to believe that QED is going to be a valid theory up to that scale. But the pole persists in perturbation theory. But I think non-perturbative calculations seem to suggest that the pole disappears if you sum up all the orders in perturbation theory.
But this number is so large because there's actually an H bar sitting in front of the log, right? That we set to 1 in our considerations right now, right?
Right. Yeah.
Yeah. Okay.
Yeah. I didn't really calculate this. I just.
No, we do this to 1 loop, so there should be an H bar. Yeah.
So, like, is there a non-perturbative calculation to actually check that?
Yeah, people have done that,
oh.
So I looked it up on the internet, and people say that the pole actually goes away when you do non-perturbative calculation. So that seems to be the case, right? But again, the non-perturbative calculation, the problem is that you're doing numerics, then several people have to do numerics in different ways for that result to be, kind of robust. So I haven't read the papers, but so Wikipedia tells me that it goes away, and then I paid $5 to Wikipedia. Oh, guys, you should all pay $5 to Wikipedia. They're not paying me for this plug. All right, so just one more comment. There's a positive sign. That means that as you increase your energy, the coupling constant increases in strength. This is in sharp contrast to what you get in QCD. In QCD, the beta function has a negative sign, which means that as you increase energy, the coupling decreases, and that's something related that's called asymptotic freedom. So that very high energy, QCD becomes essentially free. Pure non-abelian gauge theory, if you don't have matter, is always asymptotically free. But QCD, when you put matter content, it may or may not be, but in terms of QCD, it turns out to be free. But in this case, the fact that at long distances or at small energies, the coupling actually decreases. This is called vacuum polarization. And this is analogous to something that happens in dielectric, where if you have like a charge in a dielectric, it induces polarizations around, the other atoms become polarized because of the presence. And basically the effective charge that you measure is actually less than the charge that you've put in. So that's called the dielectric screening. So because of vacuum fluctuations, something analogous happens to QED, and this is known as vacuum polarization. So I'll stop here, and tomorrow Dan will tell you all about infrared effects in QED at 10:15 a.m.